So now let's talk about percent composition of compounds. So when we're talking about the percent composition, essentially we're talking about the mass percent of each element present in the compound. So in other words, we're talking about the percentage by mass, right, of an element when you take the mass of one element and divide it by the mass of the entire compound and multiply that by 100. That's basically it. So for example, if you apply that to water, what you'll find is that 11.19% of water is hydrogen and the rest, 88.79%, is oxygen by mass. All right? So we can easily determine the percent composition of elements in a formula. Very easy process. It's a two-step process. The first step is where you determine the molar mass of the compound, and we all know how to do that. Next step is that we divide the total mass of each element in the formula by the molar mass and multiply it by 100. So that's basically it. All right? For each element, you take the total mass of that element per formula unit or per molecule and divide that by the molar mass, multiply that by 100, and that gives you the percent of that element in the compound. So we can apply that, for example, to the case of hydrogen sulfide. So the question here is asking for us to calculate, whoops, okay, what is going on here? I don't know what's happening. Anyway, so first thing we need to do is find the molar mass of H2S. And let me do my little thing here to find the molar mass of H2S. And according to my calculation, this gives a molar mass of 34.08 grams per mole. All right. Then, to determine the percentage of hydrogen, that would be equal to 2 times 1.008 grams per mole divided by 34.08 grams per mole. And according to my calculations, when I do that, I end up with, divided by 34.08, I end up with 5 okay, to round this off to 4 sig figs, that would be 5.915%. And then I do the same thing with with sulfur. This time I divide the molar mass of sulfur, which is 32.06 grams per mole, divided by 34.08 grams per mole, multiplied by 100%. And according to my calculation, that works out to be equal to 94.09%. All right? So that's basically how you do that. So it's a relatively simple process. If you get the formula, if you have the formula, and to calculate the percent composition, this is basically how you would do it. Okay, now what is more challenging is doing the reverse. In other words, if you're given the percent composition, how would you determine the formula? Now, the percent composition can be determined from experimental data, which I won't get into, but you can actually perform experiments to determine the percent composition. Well, let me just go through these steps, how it is actually done, in terms of the overall process. Basically, you calculate the mass of the compound formed, and then you divide the mass of each element by the total mass of the compound, and you multiply by 100. So it's kind of similar to what happens when you determine the percent composition based on the formula. So for example, in this case, some experimental data is given, and you're asked to determine the percentage of each element for a compound formed between nitrogen and oxygen. So the first thing you do is find the total mass. So total mass is equal to 1.52 grams plus 3.47 grams, and you work that out. So 1.52 plus 3.47, and that will be equal to 4.99 grams. So therefore, percent of nitrogen is equal to 1.52 grams multiplied by 4.99 grams times 100%. So 1.52 divided by 4.99 times 100, and according to my calculation, this is equal to 30.5%. And the percent of oxygen is equal to 3.47 grams divided by 4.99 grams times 100%. So 3.47 divided by 4.99 times 100, and according to my calculation, this works out to be 69.5. And one thing I should say here, of course, and this should be self-evident, when it comes to percent composition, when you add them up for all elements, it should give you 100%, which is the case here. In some cases, you might get a number close to 100%, like 99.98% or something like that, but that's what you should get. So you can use that as sort of a check to see if your answer is valid. Okay, so as I said before, it's more difficult to calculate the empirical formula or the molecular formula for a compound based on the percent composition data. Now, what we're going to look at here is the relationship between the empirical formula and the molecular formula. Now, for us to do that, let's define firstly what we mean by the empirical formula, which is also known as the simplest formula. And this is a formula that gives you the simplest or smallest whole number ratio between the atoms present in a compound. All right? So the empirical formula gives you the relative number of atoms of each element present. It doesn't give you the actual number, but it gives you the simplest ratio of the atoms of the different elements present according to the formula. So that is the empirical formula. The molecular formula is what actually gives you the composition of the different elements present in the compound, in that it tells you the number of atoms of each element present per molecule of the compound. So for example, if you take this molecule C2H4, that's a molecular formula. So it tells you that there are 2 atoms of carbon and 4 atoms of hydrogen per molecule, but the empirical formula is CH2, because what that tells you is the smallest whole number ratio between the carbon and hydrogen, which is 1 to 2. All right. Here's another example, benzene. Molecular formula C6H6, but the empirical formula is CH, telling you that the ratio of carbon to hydrogen is 1 to 1. Here's another example, hydrogen peroxide. Formula is H2O2, but the empirical formula is HO, indicating a 1 to 1 ratio between the hydrogen and the oxygen. And here are some other examples. And what you'll notice in some cases is that you can have 2 compounds having the same molecular formula, but different, or I should say the same empirical formula, but different molecular formula. So just to highlight a couple of examples, acetylene and benzene. These are 2 different compounds. They have 2 different molecular formulas, but the empirical formulas are the same. All right. If you compare formaldehyde to acetic acid, same thing. These are their formulas. These are the molecular formulas, but these are the empirical formulas. All right. And so on and so forth. Okay. So those are just some examples showing you the relationship between the molecular and empirical formula. And in fact, here, this is just stating what I've said before. 2 compounds can have identical empirical formulas, but different molecular formulas. And here, we're highlighting the examples I showed you before. Acetylene and benzene, different molecular formulas, but their percent composition are the same because they have the same empirical formulas. All right. Now, to calculate empirical formulas, what we do is we assume that we start with a certain quantity Usually 100 grams. 100 grams is a suitable number to work with. It makes life a lot easier. But in other cases, you might be given the actual amounts. All right. Now, if we assume 100 grams, that means that the percentages would actually represent the mass of each element in grams. All right. The next step is that we convert the grams of each element into moles using each element's molar mass. And we're going to see that in the example that we're going to look at shortly. And then the third step is that we divide the moles of atoms of each element by the moles of atoms of the element that has the smallest value. If the numbers obtained at this stage are whole numbers, then we use those numbers as subscripts when we're writing down the empirical formulas. If the numbers obtained are not whole numbers, then we have to move on to the fourth step. And in the fourth step, what you need to do, and this is sort of kind of like a trial and error situation, where you're going to multiply the values obtained in step 3 by the smallest numbers that will convert them into whole numbers. And therefore, when you get those whole numbers, then those whole numbers will be used as subscripts in the empirical formula. So for example, if you end up with something like this after step 3, where these are the subscripts, 1 here for the iron and 1.5. This is not sufficient because we need integers for the subscripts. So 1.5, we have to multiply it by a small integer, the smallest integer possible, to convert it to an integer itself. That integer would be 2, so we multiply 1.5 by 2, which means that we have to multiply the 1 here by 2 for the iron, and therefore the final formula is Fe2O3. All right? Okay, so it says here the results of calculations may differ from a whole number. If they differ by more than 0.1 plus or minus, then you round off, well, within 0.1 plus or minus 0.1, then you round off to the next nearest whole number. So for example, let's say you get your subscript being 2.9, then it's okay to just round this off to 3, all right, because 2.9 is very close to the nearest integer, which is 3, all right. But if the deviation from a whole number is more than 0.1, then that means that you have to do a kind of trial and error where you multiply that number by an integer until you get a whole number. So for example, if you end up with something 0.25, that means you'd have to multiply by 4, right, to get 1. If you get like a recurring 3 after the decimal point, you multiply by 3 to get your integer. If you have a recurring 6 after the decimal point, you multiply by 2, by 3 actually. If you have a 0.5, right, if you have a 5 after the decimal point, you multiply by 2. And if you have a 7.5 after the decimal point, you multiply by 4. And these would be the resulting whole numbers from that exercise. We're going to see some examples in class so that you'll see more clearly what is being done here. All right? Okay, so let's look at some problems. This problem says, in fact, tell you what, let's stop here for today, and then the next video we'll be looking at some examples of how we derive the empirical formula for a compound. Until next time.